Our permutation functions, remember here that our permutation functions are what? They are, first of all, functions. The permutation part refers to the fact that the domain of the function and the range of the function, or technically this is called the codomain of the function, are coming from the same exact set. For a function to be a permutation function, not only do you have to have your range and domain coming from the same set, in fact, they have to be the same set exactly, and that notion of them being exactly the same set is a direct result of a permutation function being a bijection, specifically both one-to-one and onto. Onto means that you've actually reached everybody in the set after the arrow. One-to-one means that everybody in your domain gets mapped to a different element in your range. Okay, so there's, in terms of if you've done this in a graphical sense, so like back in an algebra class where you have y equals something something in terms of x's and you graph it on the xy coordinate plane, your being a function is the horizontal line test. Where you intersect your function in exactly one point. So for example, a circle, not considered a function. Why? Because here you intersect in more than one point. But if you want to be one-to-one, it's considered the horizontal line test. I'll just go through. Here, notice what's grabbing. You've got two different x values that map to the same y value. And that would be an example of not one-to-one in this infinite graphical sense. Okay. Onto simply means you've used up your entire set after the arrow. So in this case, this guy would not be one-to-one. And if this function, this roughly speaking, I was trying to get a function that looked close to x squared, it's shifted a little bit. So maybe it's actually, I don't know, x minus 1 squared. I'll just pretend it's x. If this guy was actually dealing with real numbers, if this codomain over here was a set of real numbers, the actual range here looks like the y values are bigger than, I don't know, I'm going to make up a number down here. Maybe that's a 2. Okay, something like that. I'm going to put quotes around this guy because that's not exactly x squared. That's x squared moved. Okay. But that would be the idea of pulling it back to what you would have seen like in algebra class. In terms of what we're dealing with a finite permutation function, which does all the same thing, but graphically you don't look at any of those same graphs. Okay? So on a finite set, what happens is, first of all, your building set, so your domain and range are coming from some finite set. You're still looking for one-to-one and onto, but what it actually means if we're in that first format that we saw, that was the 2-row format, was when you grab your domain, or you list them all out at the top, that second row down there is just a permutation or a rearrangement of the same set, that set A. And that's actually how you can spot your permutation function, is just the rearrangement there. And since we actually mentioned it, let me actually show an example real quick. So putting in an extra example here. Let me make this so I can write on it a little bit better. Excellent. So here, for example, suppose you have a 2-column format, so we'll call it F. It's still going to be a function. 1, 2, 3, 4, 5. That was so trying to be a 4. Maybe you have 2, maybe you have 5, 4, 3, 2. I'm going to claim that this guy, F, is not a bijection. Or if you prefer, it's not a permutation function. Anybody spot where the issue was? Yeah, it's a second copy of the same thing. So the fact that you've got those 2 2s right there, that tells you that you are not one-to-one. And in the finite case, it also means that you're not going to be onto. So we are not, I just need more space. That's all there is. Let's put in a little bit more space here. All right. So make sure I can write. Get rid of that guy. So in terms of one-to-one, now just box it so it's easy to see where we're at. We've got 2 maps to 2, and we have 5 maps to 2. So this means we are not one-to-one. And in terms of onto, for onto, we don't have anybody being mapped to 1. In other words, you don't have, you haven't actually got all your numbers 1 through 5 on that second row. It turns out in the finite case, if you are either one-to-one or onto, or you're not one-to-one or onto, automatically you either have or don't have the other one. So in this particular case, as soon as we saw that we had the doubled up copies of the 2 copies of 2 here, we're not one-to-one, bam, we're not a bijection because you're not one-to-one. You don't even have to look at the onto. But it turns out in the finite case, you're both. You got them both or you got neither. You don't have one or the other. But that would be the idea to check it. So notice what that means in terms of what we're doing. That means we have to have, in all of our work, we have to have a copy of exactly 1 copy of all of these numbers from our domain. Okay. Now, we talked about that last time. We just didn't have an example explicitly in this 2-row format. So where we got last time is we talked about the 2-row format. We looked at how to compose 2 different permutation functions. We looked at how to take the inverse of a permutation function with the 2-row format. We just flip-flop the 2 rows and then re-put it in standard form. We looked at how to take a power of a 2-row format. Don't overthink it. You just compose that number of permutation functions together, where it's specifically the 1 permutation function that you've got. And the thing that we ended on was where we gotten into our disjoint cycle notation, and we were starting to do some operations on our disjoint cycle notation. Technically speaking, we did an example, I believe, of almost everything that you can do in the disjoint cycle notation. I don't think we explicitly had an example with inverses and with powers, but it's going to be done the exact same way that we did yesterday as well. So I want to start today with doing a couple more operations with these disjoint cycle guys, or multiplying products together. So I've got a couple of examples here prepped up. Then we'll have some examples that will work together, and the thing that we're going to end on in terms of the permutation functions is we're going to look at a specific property of permutation functions. One of the standard things that people do is they look to see whether your permutation functions are even or odd. And just as a heads up, because I don't think I mentioned this last time, one of the applications of these permutation functions are dealing with what are known as symmetries. Your book actually has some really awesome pictures in it dealing with symmetries. And basically what it is where you've got different geometric shapes, and by rotating the geometric shapes or by flipping the geometric shapes, it corresponds to a different permutation function. Basically, I guess you could do something with this in terms of application of if you're doing some sort of computer graphics would be where this stuff can start to come in. Although linear algebra with matrices also comes into play with that too. So don't just have one math topic corresponding with those things. But anyway, we're going to talk about now dealing with cycles and products. Okay. So first of all, let's just remind ourselves of what to do. So we've got 2 products here that I've prepped up for us that we would like to multiply together. And notice last time what happened is I actually told you, hey, first permutation function is P, and it's this guy. Second permutation function is Q, and it's this guy, and I multiply the 2 of them together. And you can totally see that. But you can also see things like this. When you see something like this first example that has 3 cycles in it, notice there's actually a 4 in all 3 of these cycles. What it means is you can actually have one of 2 situations going on. The first situation is you're actually trying to compose or multiply 3 different permutations together. One that corresponds with the first cycle, one that corresponds with the second cycle, and one that corresponds with the third cycle. And that's something that totally can happen. And if you wanted to write these guys into the 2-row format, you totally could. Before you do that, though, you do have to know what your building set is. And we always assume that our building set, unless told otherwise, is going to be, in other words, our domain, the numbers 1, 2, 3, up to whatever the biggest number is among your cycles. So in our case, what should be our biggest number in our building set or in our domain? You guys spot the biggest number? 7? Yep, it does look like a 7. There you go. So this one, we'd just be looking at our numbers 1 through 7. So when we go and track out what the actual answer is, we'll want to make sure that we grab our numbers 1 through 7. So it actually, in this particular case, you have to include the numbers 1 through 7 because, well, I guess technically 3 isn't listed in all of those numbers. But if you're told otherwise, you could also, and I'm going to erase this, so if you want it down, you'll need to write it down. You could be told, hey, my building set or my domain is actually all of the numbers 1 through 9. Notice that's also perfectly legitimate. There's nothing in these cycles that tell you you can't have the domain of 1 through 9 or the building set of 1 through 9, but both 8 and 9 are not visible in any of those cycles, which means in our answer, when we actually multiply all of these guys together, you're going to have whatever answer we get from the 3 cycles we have, and then at the end, you'll have the 1 cycles of 8 and 9 because they're not visible right now, okay? So what that means is, unless you are told otherwise, you just grab the biggest number visible in your cycles and say, hey, maybe there's a bunch of 1 cycles at the end, but I wasn't told that, so I'm going to assume that there are not those 1 cycles at the end, okay? So and that is, it's just a standard thing just so you know where to stop is basically what it is. But what I try to do for you guys when I make these problems, and I realize that in homework I don't actually make the problems, I'm pulling them from the book or another resource. Sometimes they will give you what the building set is, this A, and sometimes they will not. So this is the strategy if you're not given what that building set is. Okay. And I'm going to erase this middle stuff right here. So if you need it still there, let me know before I hit the erase button. Whoops, that was not the button I was going to hit. All right, seeing nobody yell, I'm just going to go ahead and hit delete. All right, so that was one thought, is they could actually be 3 different cycles you were composing together. Here's the other option. The other option is it actually is either one permutation function that was just written stupid. Why? Where all of the cycles were not disjoint cycles. So standard form in terms of your product of cycles is the cycles have to be disjoint. We talked about disjoint before with respect to sets. And what did it mean with respect to sets? It meant your elements couldn't be shared across the sets. Same deal here. Disjoint cycles mean you cannot have any of the same element across more than 1 cycle in your 1 permutation. So this here, since there is a shared element of 4 across all of these cycles, it means it's not the standard disjoint cycle notation. And in terms of how you convert it into that disjoint cycle notation, you basically treat it like it's 3 different permutation functions that you multiply together, or excuse me, you compose together. Okay, so let's actually do it. Remember the deal with your product of when you do your product or your composition is we're going to read right to left, so opposite of what you normally read in English. And in terms of what you do, you always start with the lowest value. So in this case, I'll go ahead and put scratch work over to the side here. Your lowest value in play here is a 1. And what we're going to do is we're going to track where that 1 goes through each one of these permutations, or each one of these cycles. So 1 gets mapped to 4 in that rightmost permutation, or that rightmost cycle. Now, 4 gets mapped to 5 in the middle permutation, and there is no 5 in the last cycle right there, so 5 stays 5. which means in this final answer of the full composition, 1 gets mapped to 5. Okay? Now, next number you look is, to put this in cycle notation, you need to know who 5 gets mapped to. So you do the same thing. The rightmost cycle has no 5, so 5 stays at 5. The middle cycle has a 5, 5 gets mapped to 6. There is no 6 in the leftmost cycle, so 6 stays at 6, which tells you 5 gets mapped to 6. What do you guys think 6 would get mapped to? Yep. So 6 gets mapped to 7 in that first cycle. Middle cycle, there is no 7, and leftmost cycle, there's still no 7, so 6 gets mapped to 7. What do you guys think 7 gets mapped to? Yep. So here, in the rightmost cycle, 7 gets mapped to 1. Middle cycle, there is no 1, so 1 stays the same. And the leftmost cycle, 1, oh, almost. 1 actually is going to change. So 1 here would get mapped to 4. So this tells us our 7 is going to get mapped to 4. Then we grab our 4. Any guesses what 4 would get mapped to? And don't forget to go through all 3 of those cycles. Close. I think you read your cycles backwards, though. So starting at 4, 4 gets mapped to 6. In the middle cycle, 6 wraps around to the beginning, so 6 gets mapped to 2. And in the leftmost cycle, the one here on the end, 2, there's no 2, so 2 stays at 2. So then we want to see what 2 gets mapped to. What do you guys think 2 gets mapped to? All right, I'll go back and answer that question in just a second. Let me go ahead and finish this line with a 2, and I'll grab the second line with this bit right here. So in terms of what we've got here, we've got 2. Well, there is no 2 in that cycle, so 2 stays at 2. In the middle cycle, 2 gets mapped to 4. And in that leftmost cycle, 4 gets mapped to 1. And let me actually label these because I think it will be helpful. If we label this as P, Q, and R, this first arrow right here is us traveling through the relation R. This second arrow for all of them is us traveling through the relation Q. And this last arrow right here is us traveling through the relation P. And technically, I just labeled the cycles. So you said second line, and I just closed this off without writing the 1 here because we started off our cycle with a 1. Okay. Now, in terms of this line, so this is the one that you guys are asking about, and then that one. So the 6 mapped to 6, this was inside our cycle that was the 2 cycle here. So we came in on a 6. There was no 6 at all in this 2 cycle, so no change in the 6 here. However, this 6 getting mapped to a 7 was actually inside a different cycle. So in this other cycle, there actually is a 6, and this time the 6 got mapped to a 7, which is why you got the 6 mapped to a 7. And if you're tracking 6 all the way down, we actually had 6 in a third place as well. This 6 got mapped to a 2, and this 6 got mapped to a 2 because we were inside of that middle cycle at the time. The 6 here gets wrapped around and mapped to that 2 at the beginning of the cycle. So those different arrows represented which cycles we were in. So in the different cycles, you're going to get the same number mapped to potentially a different number depending on which cycle you're in. And that's one of the reasons why I definitely should have labeled these arrows ahead of time. And if you're doing this on your own scratch work, you might very clearly label what all of those arrows are just so you don't get turned around. Now, let's finish this off. We said our building set or our domain was the numbers 1 through 7. Do we have all the numbers 1 through 7 in the cycle we just built? And if the answer is no, who's missing? Correct. So we're only missing 3, which means when we start our next cycle, you start the next cycle with the smallest number that you haven't used yet, which is a 3. But 3 is the only number you haven't used yet, and 3 is completely missing from these cycles here, which means that tells you that 3 is a little 1 cycle. So if you didn't want to write it at all, you didn't have to. And that's how to take a product of not disjoint cycles, or cycles that have overlapping or duplicated terms, and putting them together in the standard disjoint cycle notation. And you can think of this as either, like we said before, 3 different permutations that you're multiplying together or technically composing together, or you can think of it as 3 cycles that are inside the one permutation itself. Both are things that you would need to do dealing with permutation functions. And in terms of this class, it just would be a different setup of the problem. So any questions on that example before we do the exact same thing on this next example? Okay, well in that case, let us do the exact same thing, but now we just have different numbers. And I on purpose chose this second example because the example that we have right here, when we actually did this operation and combined the 3 different cycles together, we got one ginormous cycle, which does totally happen, but it also happens frequently that when you compose all these guys together, your answer isn't just one big cycle with maybe a couple of 1 cycles hanging out. So let's see what would happen if you don't get that, and how to start your next cycles. Okay. So again, I'm going to put scratch work over here to the side so we can track what we're doing. And let me go ahead and label the arrows here a little bit better than what we started off with in the other one. So when we multiply together, you're going to multiply always right to left, so it feels backwards. I'll go ahead and label these the same P, Q, and R as before, just so we have labels on which cycle is doing which, especially since I can't say a 2 cycle and a 4 cycle because we've got 2 4 cycles. Okay. So first thing you always do is you start with the absolute smallest number in your domain. And in this case, our domain is going to be the building set 1, 2, all the way up to, it looks like our biggest number here is 8. So if we start with 1, first we're going to be inside of the 4 cycle that's labeled with an R. So let me label that arrow with an R. And here there is no 1 whatsoever, so 1 gets mapped to 1. Now inside of the cycle labeled with a Q, there is a 1, so 1 gets mapped to 2. And inside the cycle, the 2 cycle, there is no 2, the number we're currently looking at, so 2 stays the same. If the number isn't visible, it stays the same. Okay. So then, what do? I feel like I'm going to need more scratch work than I allowed myself. Next, we'll look at a 2. In the first relation, or I should say the 4 cycle here labeled with an R, 2 gets mapped to 4. In the middle cycle, there is no 4, so 4 stays the same. In the last cycle, there's also no 4, so 4 stays the same. And I'm going to give ourselves a little bit more space here. Did not account for scratch work. So, next thing we do, don't undo, no. Push the wrong button. So next thing we do is we look at our 4 and see where 4 gets mapped to. In the cycle labeled with an R, so the rightmost cycle, 4 gets mapped to 6. In the middle cycle, there is no 6, so 6 stays the same. And in the leftmost cycle, there's also no 6, the 4 gets mapped to 6. And then you keep repeating the process. So in the cycle labeled with R, 6 gets mapped to 8. Middle cycle, there is no 8. And cycle labeled with the P, so leftmost cycle, 8 gets mapped to 5. But I made sure to get this one broken up. I am now concerned. Okay. So then we look at where 5 gets mapped to. In the rightmost cycle, there is no 5, so 5 stays the same. In the middle cycle, there is a 5. 5 gets mapped to 1. And in the leftmost cycle, there is no 1, so 1 stays as 1. And when we got back to 1 right here, that's the same starting as our starting point, so that closes off the cycle. And don't write down the actual 1. Now, our building set was the integers 1 through 8. We have not used all of them yet. So who's the smallest integer that we haven't used yet in our domain? Regardless of whether you can see it in those cycles or not. Correct? It's a 3. So new cycle, and now we start it with a 3, and we just repeat the process. So we look to see where 3 gets mapped to. In that rightmost cycle, there is no 3, so 3 stays the same. Middle cycle, there is a 3, so 3 gets mapped to 5. And in that leftmost cycle, there is a 5, so 5 gets mapped to 8, which means overall 3 goes to 8. That was a terrible 8. Hopefully your 8s look better if you're writing this down. So then we look to see where 8s are going. Rightmost cycle, 8 gets mapped to 2. Don't forget it wraps around. Middle cycle, 2 gets mapped to 3. And in the cycle P, there is no 3, so 3 stays at 3. And notice right here, because we started with a 3, that closes down our cycle. Now, who is the smallest number left in the domain that we have not used, or have we used up everybody? Yep, we totally have a 7 left. Now, question for you. Are there any numbers other than 7 left? There are not, which means 7 has to be a 1 cycle. So let's go ahead and double check that. In terms of 7, notice it is not visible in any of these cycles. So that means none of those cycles are going to change 7, which means you are going to get a 7 all the way through. And that is what happens if you have a 1 cycle. You start and you stop at the exact same place. Which means this guy, if you didn't want to write down the 1 cycle, you totally could. We just leave it off. And we would get that if we actually combine those 3 cycles together that were originally not disjoint, you'll get 2 disjointed cycles, 1 a 2 cycle and 1 a 5 cycle there. Okay. Notice I just completely ignored the little 1 cycle. It's perfectly fine to keep it, and when you're first starting, I would recommend keeping it, but it's standard to just leave it off. Again, it's like what we said last time. It's similar to, say, 1 times x in like an algebra equation. It's okay to do it, but you don't normally, unless you're just first starting out. Or you accidentally wrote a 1 and you were too lazy to erase it. Okay. So that's the basics for multiplying these guys together with the permutation functions. I wanted to make sure to get those 2 examples just so that you were comfortable with what happens if you actually got 2 properly distinct cycles here and not just some 1 cycles. Right to left. Yes, in terms of so this is where these things can get screwy when you're first starting out. In terms of the cycle, so there's 2 levels. When you're dealing with the individual cycles, it's always right to left, so following this big arrow. I still put that arrow in there just to make sure I'm progressing through the cycles and don't accidentally go reading it like normally across a printed sentence type thing. But inside of the cycles, you go left to right. So let me actually write that down. Reading the cycles, you want to go this way, but who gets mapped to who, so that's inside the cycle, and you're still reading left to right, if that helps. I realize that might be a little vague, so hopefully it's enough to clue in of what we were talking about. But yes, it's always right to left on the cycle level. Other questions about dealing with these guys? We're going to have more examples, but okay at least following it when somebody else does it right now. All right, so let's get an example, another example. So this next example, I went ahead and put it into the back into the 2-row format, and I'm leaving the other stuff up there a little bit in case anybody's writing down and still needs it. So this one here is written out a little bit different than before, but it's similar to something that we talked about last time. So this one here wants us to do what? We have some permutation function, and we would like to raise it to a power. It doesn't tell you which power to raise it to, but it wants to find what's the smallest power that you can actually put on your permutation function and get back the identity function. Now, there is more than one answer to this. Okay? So here's the answer that nobody wants. K equals 0. Okay? So by definition, any permutation function raised to the 0 power is going to be your identity function. This totally mimics what you do if you were raising any integer to a power of 0. For example, 3 to the 0, always 1. Anything raised to the 0 power is always 1. Here, in dealing with functions, we don't have a function that is 1. Instead, we have the identity function. But how would we know that k equals 0 isn't the answer that we want? There's something in the wording of that question that's going to tell you we don't want k to equal 0. Anybody spot the buzzword? Why could I tell you that for k here, k has to be bigger than 0 for this particular statement? What's the key word there that makes you know that? Yes, smallest positive integer. The integer tells you it's got to be an integer. The smallest means get it as small as possible. That because there's actually going to be more than one answer, so you want the first one you get to. But it's the positive part right here that is going to tell you, hey, you're not allowed to pick k equals 0. I'm sorry, you can't get away with the easy answer. Okay? So how would we actually determine this? Well, it turns out you can totally answer this question just by brute forcing it. Find p squared, find p cubed, find p to the 4th, and find the first time when you actually get your identity. Okay? Now you can do this in the 2-row column format, not column, 2-row format. We did this last time, and I accidentally actually gave you a permutation that when we squared it, it turned out to be the identity. In that example from last time, this k would have been 2 because we squared it, and that was the first time we got to be the identity function. In this particular case, I wanted to show you that same sort of thing of taking powers, but specifically in the disjoint cycle notation. So let's first go ahead and convert this guy into its cycle format. So if we convert this guy into its cycle format, always start off with a 1. So we have 1 is mapped to 2. 2 now is mapped to 6. 6 is mapped to 3. 3 is mapped back to 1, so we close that cycle. You pick the smallest number that we haven't used yet, which in our case is going to be who? Or maybe I just open this up to you guys. What number should be in this second cycle? So what should I write after 4? Is 4 going to be a 1 cycle, or do I need to put something after the 4? Yep, 5 would go after the 4. And if we look at 5, 5 gets mapped back to 4, or the other way to check it is there's only 6 numbers anyway. So once we had 4 and 5 in that same 2 cycle, we're going to have to close it off. Okay? So this was our same guy in the 2 cycle notation. Please note, anytime you're given either notation for your permutation function, you can always convert it back to the opposite format for your peace of mind and or sanity, depending on which one you like better. Okay? You will often see the disjoint cycle format written out a lot just because it's easier to typeset. Okay. However, when you're first starting, a lot of people really like the 2-row format. Totally fine if you always take these guys and convert back to the 2-row format. Totally fine. Okay. In the homework that's associated with this, there are 8 questions, I believe. Half of them give you the 2-row format. Half of them give you the cycle format. And I have to admit that the exact same questions, almost, different permutations. But they ask you the exact same things, and it's just which format you originally were starting with. Okay? But be careful in terms of entering the answers because you can't actually type that format well, so it's going to give you a way to type it up. Okay. So let us actually figure out the powers, and I'm going to brute force this, and then we're going to show a shortcut way of figuring out what that value of k is. So first of all, let's look at p squared. So p squared is where you take your permutation p and you compose it with itself. So in terms of this cycle notation, literally just set 2 copies of p next to each other. Now, we just looked at multiplying these guys together. I'm not going to do the scratch work, so pay attention. This is going to go a little bit fast. Okay? So I'm going to go ahead and multiply these guys out. Let me do a little bit of scratch work here so we'll see where it goes. Let me actually just make that thing be down. That way I can color code things and write it in black at the same time. Okay. So we'll always start this guy off with, and then I have it color coded too early. So we always start off with a 1. So we track where the 1 lives in the actual cycles. Remember, we are going right to left. So we find our 1. It's not in the rightmost cycle. Next one over, it's right here. So 1 gets mapped to 2. 2, not there. 2 gets mapped to 6. So overall, 1 goes to 6. And if you always want to write the scratch work to the side, definitely do it. I'm just not going to do it right now. Then we look where 6 goes. In this particular case, we have 6 right here. That's the first time reading right to left that we see a 6. 6 gets mapped to 3. Hold in your head 3. There's no 3 on the next cycle. 3 here now gets mapped to 1. 1, notice, was where we were at before, so we closed the 2 cycle. Next smallest number we haven't dealt with yet with is 2. So we look for 2 in our cycles, always reading right to left. It's not in the first cycle we see. Second cycle we see 2 gets mapped to 6. So here's our 6. Hold in your head 6. 6 is not in the next cycle. 6 is in this cycle, and 6 now gets mapped to 3. So we write down the 3. Don't write down your number until you get all the way through your cycles. Biggest mistake you can make at this point in seeing these cycles. So next we look at 3. 3 is not in the first cycle on the right. 3 is in the second cycle we see, so 3 gets mapped back to 1. So hold in your head 1. 1 is not in the third cycle. In the last cycle, 1 gets mapped to 2, so we close off that 2 cycle. Smallest number we haven't dealt with is a 4. 4 is in the first cycle, the rightmost cycle. 4 gets mapped to 5, so we hold in our head 5. 5 is not in the second cycle. 5 is in the third cycle, so 5 gets mapped back to 4. Hold in your head 4. 4 is not in the last cycle, so this gets closed off and is a 1 cycle. Last number we haven't used is a 5, so it better be a 1 cycle or we screwed up. So if we read right to left, 5 gets mapped to 4. Hold in your head 4. There's no 4. Here's a 4. 4 gets mapped back to 5. Hold in your head 5. There is no 5 in the last cycle, so we close off our 1 cycle, and this gives us in standard form 2 cycles of 1, 6, and 2, 3. So that would be p squared. Note, p squared is not the identity, so k can't equal 2. So that means we have to keep going. So p cubed is the same as p squared times p. So we'll write down p squared, which is 1, 6, 2, 3. We write down p, which is 1, 2, 6, 3, and 4, 5. And then we'll do the exact same thing. Okay? So this time, we start with a 1. We'll read right to left, so let me put the arrows in. When we look at our 1, the first time we get a 1 is in the second cycle, reading right to left. 1 gets mapped to 2. We then look for 2. 2 gets mapped to 3. There is no 3 in that last cycle, so 1 gets mapped to 3. Then we look for 3. Notice here, 3 is only in this second cycle that we're looking at, right to left. 3 gets mapped to 1. Hold in your head 1. There is no 1. Last one, there is a 1, so 1 gets mapped to 6. So we write down the 6. Notice it's tedious, but there's not any difference in what we're doing than what we were doing before. Just not writing down the scratch work part. Now, once you have a 6, we'll track where the 6 goes. The first time we see a 6 is right to left, the second cycle we see. 6 gets mapped to 3. So we look now for a 3. 3 gets mapped back to 2, so we're looking for a 2. There is no 2 left, so we're going to write down a 2 in our actual answer. Then we track our 2. So there's no 2 in this rightmost cycle. There is a 2 in the next cycle, so 2 gets mapped to 6. No 6. 6 gets mapped back to 1, so we'll close off and get a 4 cycle. Then we look for the smallest number in play that we haven't used yet. Smallest number we haven't used is a 4. So we look here and we say, all right, well, what's happening? 4 gets mapped to 5. Well, there are no other 4s and 5s, so 4 just gets mapped to 5. And at this point, you're going to have to close off because that's the last number. So that's p cubed. Making sense? Kind of okay so far. So we didn't get the identity function. So we do it again. So now we look at p to the 4th. Now p to the 4th, you could do p to the 4th 2 different ways. You can either say it's p cubed times p. What's the other way that you could figure out p to the 4th? In other words, p to what power times, oh, there it goes. Yep, p squared times p squared. Do you guys have a preference which way we actually compute this? I can tell you which one my preference would be in terms of less work. Yeah, that's the one I would choose too. So if you've got somebody that's got a bunch of 2 cycles in it, it turns out that's typically the way to go in terms of less work. And I'll give you that property once we do what we're about to do. So 2 copies of p squared coming up. So our 2 copies are 1, 6, 2, 3, and then a second copy of 1, 6, 2, 3. Now notice how many numbers are in play right here, okay? We don't actually have all of the numbers 1 through 6 in play. We only have 4 of those numbers in play. We've got 1, 2, and 3, and then 6. You visibly do not see either 5 or 4. And if you don't visibly see either 5 or 4 in the current 4 different 2 cycles, what that means is 5 and 4 are going to stay as 1 cycles in the final answer, okay? So we're not even going to have to worry about 4 and 5 right now. Let's worry, though, about the guys we actually see. So we always start off with smallest number haven't used yet, so that would be a 1. And if we track our 1, notice 1 is reading right to left in the second cycle, so 1 gets mapped to 6. And then we're looking for a 6. Well, we don't see 6 till the 4th cycle, and 6 gets mapped back to 1, so we got a 1 cycle at 1. Next number that we haven't used is a 2. Any guesses what happens with a 2? Do you think 2 is a 1 cycle, or if it's not a 1 cycle, what's the number that 2 gets mapped to? Yep, you totally got it. 2 is going to be another 1 cycle. So 2 gets mapped to 3. 3 gets mapped back to 2, so we close off the 1 cycle. And if we look at 3, which is the other number in those 2 cycles, you're going to have the same result. 3 gets mapped to 2. There's no 2s other than in this next guy, and 2 gets mapped back to 3. We already said both 4 and 5 will be 1 cycles because they're not visible. And any guesses what's going to happen to 6? Do you think it's going to be a 1 cycle? If it's not going to be a 1 cycle, who do you think 6 is mapped to? So this guy is going to end up being a 1 cycle again. And part of that you can see just because it's the last number that we haven't dealt with yet. And part of that is you actually, if you track it down, it'll be a 1 cycle. 6 gets mapped to 1. No 1s, no 1s. 1 gets mapped back to 6. That's the result that you get for an identity. Because remember, you don't write down 1 cycles, except in the identity function. You have to write down at least 1 of those 1 cycles, and we picked the smallest one, which is that 1 cycle of 1. Which means, what's the answer for this particular question? In other words, what k value, what smallest positive integer for k, would give us back the identity function? What do you guys think? What's the answer here? Yep, don't overthink it. It's totally that exponent that we were just dealing with. So our answer here, and let me go ahead and get rid of that top part so you can see more of it. So our answer is k equals 4 right here. Now, it turns out that you could totally have done all of this same work in the 2-row format, but I personally think it's easier to do it in the cycle format, and not because of all of that work. It's because of an interesting fact. So second aside. And let's actually make this aside a different color. If you have 2 cycles, I'm going to claim that that is always going to give you the identity function. Why? Because if you track down what happens with 1, 1 gets mapped to 2, 2 gets mapped back to 1, and same thing happens with the 2. Turns out if you have a 3 cycle, if you do this 3 cycles, where they're all the same copy of each other, notice what happens. Your 1 gets mapped to 2, your 2 gets mapped to 3, your 3 gets mapped back to 1. And the same thing will totally happen with the 2 and the 3 as well, which means you'll get the identity function. Anybody extrapolate from that a guess on how many copies of a single cycle you would need in order to break it up into an identity, or only 1 cycles, if you will? So say you have an n cycle. We'll call it p. P to what exponent up here gives you only 1 cycles. And remember, n is the number of numbers in the cycle. So an n cycle means you have n numbers in the cycle. Or this was a 2 cycle and a 3 cycle. You got it. And that is a fast and dirty way of figuring out what the exponent is of your permutation function needed to break down that permutation function into only 1 cycles. And remember, only 1 cycles is going to give you your identity function. So using that information, see if you guys can figure out a guess for this next question. And I went ahead and put this one up on poll everywhere. It is currently active and visible for you guys. I see several of you already found it. Let me go ahead and share it on the side. I know that's going to make this super tiny, but just to give you the URL if you didn't remember it and you're logging in through a website. This is the same link that we've used throughout the course. If you've already got it on an app on some other device and you've already got it logged in, same place. Okay. I'll give you guys a second to see what's going on. Notice in terms of your total building function, regardless of how your cycles are broken, just by raising your permutation up to the I'm not going to say that because there are some exceptions. So pretend I didn't start saying something. So I'll give you guys a sec to make a guess there, and then we'll see if we can't figure out what's going on. All right, it looks like about half of you have made a guess. Ooh, it's starting to creep up. Please note, we aren't leaving you guys quite enough time to actually brute force this. So I'm not expecting you to actually multiply that thing out a whole bunch of times to figure out K. The goal here was to try to do it a shortcut way. Although if in the future you don't remember the shortcut way, that's okay. You can always brute force it. That has definitely happened on tests a number of times in past semesters. Nice thing about having more than one way to solve a question. All right, it looks like most of you guys have an answer, so I'm going to go ahead and stop showing that. Actually, I'm going to stop showing that second screen. Oh my, and the answers are all over the place. So let us work through it. Okay. So in terms of what we know, so from the shortcut, what do we know? We know that if K is a power of 2, I shouldn't say K is a power of 2. If we have 2 copies of our 2 cycle, it'll split into 2 1 cycles. Okay. Now, how many copies of our 3 cycle would we need to split it into 1 cycles? You'd need 3 copies. So you need to have some way where you have both 3 copies of the 3 cycle and 2 copies of the 2 cycle. So anybody have a guess what number would give us both 3 copies of the 3 cycle and 2 copies of the 2 cycle? Or multiples thereof. So that's actually the trick, the multiples thereof comment. Ooh, we do have a winner. So if you only have P3, notice what will happen. You'll have 1, 2, 3, 4. You'll have your 3 cycle. You'll have 3 copies of your 3 cycle. 1, 2, 3. So that guy will split up, no worries. You'll have 2 copies of your 2 cycle. So those guys will split up into an identity function just fine. But notice you still have the 1 extra copy of the 2 cycle. This guy, if you actually multiplied it all out, would give you that 2 cycle of 2, 3. Okay? But you still have to have 3 copies of the 3 cycle in order to get the 3 cycle to break up into 1 cycles. So if we bump this up into P6, that would give you 6 copies of each of these guys. So you'd have 1, 3, 4, 2, 6. There's one of them. 1, 3, 4, 2, 6. 1, 3, 4, 2, 6. So here, your 1, 3, 4 would break up into 1 cycles, in other words, identity functions. Your 2, 2, 6s would break up and you'd still just have a 2, 6 like before. So that's 3 copies. Remember, there's 3 more copies. So 1, 3, 4, 2, 6. 1, 3, 4, 2, 6. 1, 3, 4, 2, 6. And same thing happens. The 3 cycles break up into the identity, and the 2 cycles break up into an identity. So you're only left in the second part with that extra copy of 2, 6. In other words, the same thing as if you just did peak cubed times peak cubed. Now, you've got 2 cycles multiplied together. This means these guys break up into only 1 cycles, and that will give you your identity. Now, notice how could you grab the 6 just from your 2 cycle and your 3 cycle? This 6, so answer, let me move a little bit more space here. So answer, K equals 6. It's the least common multiple of the 3 and the 2. This is your 3 cycle, and that comes from your 2 cycle. That is a quick and dirty way to figure out what that smallest value of K is. Now, why is that interesting? It's because of this property. So using the same permutation, so this is like a part 2. Suppose you're asked to compute, I don't know, maybe I'm making this number off the top of my head. Compute that permutation raised to an exponent of 122. Let's not do that by hand, shall we? So, why would I say that the work we just found in the previous example right there would actually be really helpful if we needed to compute that power? Anybody have a guess? It's totally a factorization issue. How many times does 6 go into 122? It's not evenly. Anybody recall? If you divide 6 into 122, what would your answer be? Yep. And it turns out the 20 isn't the thing we're really focused on. The thing we're really focused on is the remainder. Exactly. There's the +2. So what this means in terms of exponents is this power of 122 can be rewritten as p to the 6, 20 copies of them, and then you have an extra p squared. Which means what? Because this first part was the identity, this is exactly the same thing as just p squared. So then the only thing you have to compute is p squared here. And since there's a 2 cycle involved, the 2 cycle disappears and you're really just squaring the 3 cycle, which in this particular case would end up being 143. But that's just because I know shortcuts of squaring 3 cycles. Okay. So notice that's one of the advantages of finding that power of K is if you needed to, for whatever reason, find some sort of exponents of your permutation functions, you can save yourself a buttload of work. Okay. Note, if for some reason you were coding this in You just take your mod function because you care about that remainder, and then all you're doing is multiplying or raising a power that's that mod function or that percent sign, depending what programming language you're in. Actually, I can't think of a single programming language where it's not, but there's probably one as soon as I say that. Okay. Questions make sense? Feeling kind of okay so far? All right, I'm going to go with kind of okay because I'm not seeing any questions come in. So let us do the very last thing, which is identification of even and odd permutations. So in order to identify whether a permutation is even or odd, we have to deal with something called a transposition. A transposition is simply a really fancy way of talking about two cycles. Okay, that's all a transposition is. It's actually a descriptor because you've transposed or you've swapped two elements is where the name comes from. Now, it turns out every permutation can be written as a product of transpositions or a product of two cycles. The caveat to this is, while every permutation function can be written as a product of two cycles, there is absolutely zero guarantee that that product is a disjoint cycle product. In other words, you may have to write it in non-standard form to get those two cycles. So let's see what we would do here. Oh, so this is just an example. The transposition is a two cycle. Oh, and that's something we actually just talked about, so I'm not going to talk about that one again right here. So we actually just dealt with it. I guess I jumped the gun a little bit earlier. So this one here, we talked about those two, so I'm going to skip out on those two guys. All right. So if you want to write a permutation as a product of transpositions, first of all, starting off, and this is the algorithm, then we'll get into examples of what to actually do. Okay. So if you've got some permutation, if it's already written as a product of two cycles, don't do anything. If it's not written as a product of two cycles, take any of your guys that are not two cycles, and we're ignoring one cycles here. So these are guys that are cycles of length 3 or big or longer. Okay. So for each of the cycles that's length 3 or bigger, here's what you do. You take the original cycle. So I went ahead and labeled this with a subscript K, so some arbitrary K here. And what we'll say is you take the first element in your not two cycle and write it first. And you take the last element in your not two cycle and write it second. And then you walk backwards. So in terms of how you grab those elements, you're literally grabbing the last one and then walking backwards to your final two cycles, or your final transpositions would be first guy from the original cycle and then the one right after it. This is not the same as what your author writes it out. There are two ways to do this product of two cycles. This one here is the one that you see more commonly than the one that's in your textbook, but both of them will work. Okay? Now, let's actually apply this. Okay? So suppose you have some permutation function, and it's got a grand total of 3 cycles in it. For rewriting this as a product of transpositions or a product of 2 cycles, you actually don't even have to know what your domain is. But if we look at that, I see that the highest number involved is 9, so the domain would be the integers 1 through 9. Notice of the 3 cycles currently visible, and it looks like we're using all 9 numbers. On the 3 cycles currently visible, one's already a 2 cycle, so there's no change. But we've got a 3 cycle and a 4 cycle, so those two we're going to rewrite as 2 cycles. So don't overthink it. Okay, your 3 cycle, you'd write it as a 1, and then you start from the end and work backwards. So 1 and then a 4, and then a 1 and then a 3. Now let's check to make sure that this actually works. If you actually multiplied this guy out, and this is the transposition that we actually want to use, but we don't want to replace a 3 cycle with something it doesn't really equal. Notice what happens. By not being disjoint, these two things are tied together, so if we multiply through 1 times 3, well, there's no 3's here, so 3 stays. Then we have 3 times 1, The 1 links you to the next 2 cycle, and then 1 gets mapped to 4. And that thing, when we track 4, 4 is only in that second 2 cycle, that 2 cycle on the left, so 4 would be mapped back to 1 and the cycle closes. Okay. Now, with the original 2 cycle, the 2, 8, no change. But with the 4 cycle, I'm going to let you guys figure out what this one should be. It is 5, 9, 7, 6. What would be the 2 cycles we need to write down? So to make our lives easier, what would be the first 2 cycle we should write down? Hint, it's going to start with a 5. What do you guys think? What should be the number after 5? Yep, so, oh, nope, not 5, 9. That would actually be, so how you grab it and highlight, you're always going to work your way backwards. It's not adjacent or the one that's the consecutive number. It's always the number furthest away. So you start each one of these 2 cycles with your very, very first number from the original much longer cycle. So each one of our 2 cycles is going to start with a 5. And then you reverse the order of the next 3. So 9 will be the last one. What do you guys think will be for the first one? It'll be 5 something. What's that something? Close. That'll be the middle one. The 5, 7 will be the middle one. 5, 6, there you go. So always start with the very, very last number. Don't overthink it. Okay? And then work your way backwards. Or if you prefer, if you want to write it in order, start writing it from the last cycle and then work your way backwards. Both of those 2 techniques work. Now, assembling this scratch work tells you that what? It tells you that we're going to replace our 3 cycle of 1, 3, 4 with the 2 cycle 1, 2 and the 2 cycle 1, 3. The 2 cycle 2, 8 stays the same. And then the 4 cycle gets replaced with that thing we just built, which is 5, 6, 5, 7, and 5. That's trying to be a 9, 5, 9. Okay. And that's how to write a permutation as a product of transpositions. Now, here's why we care. If we need to identify, for whatever reason, an odd permutation or an even permutation, you need that transposition, because here's how you define odd and even permutations. P is odd if it can be written 2 T's as a product of an odd number of transpositions. Any guesses what the definition of even is going to be? You mean the exact same thing with 1 change. Any guesses what that 1 change is? Yep, even number of transpositions. That's literally it. So the only reason we care about these transpositions is literally so we can count them to get whether the permutation's even or odd. So what do you think? In the permutation from the example that we just did, do you think that's an even or an odd permutation function? So it's this guy right here at the top of the screen. What do you think? Is that last one we just did even or odd? Don't overthink it. You just count them up. So we have 1, 2, 3, 4, 5, 6 transpositions. 6 is an even number. So this guy here is considered an even permutation function. That's literally it. Just count the number of transpositions. I think I have one guy prepped. So yeah, so for this guy here, is it even or odd? First thing that you would do is you rewrite it as a product of 2 cycles. So with this first one, we're going to rewrite the first 4 cycle as 1, 7, 2, 4. Notice on these last 3 numbers, I just reversed their order. That's literally all I did, except I needed to make them cycles. Just a second. Backing up. So 1, 7, 1, 2, 1, 4. If you just reverse it the way I did, it's actually the inverse in terms of cycle notation. We'll do the same thing with the 3 cycle. Reverse the order of those last 2 guys. So we'll have 3, 8 and 3, 5. Make sure they're actually 2 cycles, and nobody cares about your 1 cycle. Okay? So what do you guys think? Is this permutation function even or odd? So this one here, count up your number of transpositions or your number of 2 cycles. You'll get 1, 2, 3, 4, 5 of them. 5 is an odd number, so the answer here would be odd. And that's all you got to worry about doing. Okay? So that's it in terms of permutation functions. Based on the current time, let me actually go ahead and throw us into our example today. And based on the current time, that's probably what we'll end with. So we'll start tomorrow with posets, and we will deal with posets for the rest of the course. Just as a heads up, in terms of posets, they are going to be dealing with, actually let me get you the definition, and then we'll actually deal with posets for real next time, okay? So in terms of posets, the things that you're going to want to deal with is we're going to go back to relations. They're not going to be functions. The thing that you want to make sure that you have in front of you when we deal with posets tomorrow is a partial orders of relation that's reflexive, antisymmetric, and transitive. So if you don't remember what those 3 properties are, you'll want to go and look them up. So reflexive, antisymmetric, and transitive. If you need to write them down, write it down real quick. Okay. We'll go back over this again tomorrow, but those are 3 that you want to have in front of you. We're going to talk about posets, which their official name is a partially ordered set. That's almost like an acronym, the poset. And it's going to be where we look mainly at the set, but the actual elements of your set interplay with each other or interact with each other by way of the relation that's considered a partial order. And what we're going to look at is we're going to look at the picture representation of how those guys are put together, which is called a Hasse diagram, and then some of the things that we can do together with it. So this one's going to be very graphical because we're going to be dealing with that picture a lot. But I wanted to give you the heads up of where we're going. That way, if you wanted to look up those 3 properties beforehand, totally can go for it. But this is going to be going back to graphs more. Okay. But for the rest of today, I'm going to throw you guys into dealing with groups. So the thing that you need in order to deal with this group activity is if you didn't grab the activity 10 that was posted on Canvas today, that's okay. Because what I did is I threw all of those directions, and I'm going to share this second thing with you guys. I threw all of those directions up here on, and I know you can't read it, up here on this Whiteboard thing that we dealt with last time. Now the link to this Whiteboard, and I'll copy and paste it and put it in the chat here in just a second, but the direct link to this particular Whiteboard is actually up on Canvas. It's right under today's date in Canvas, and it looks like a couple of you have already found it. Just like last time, you can totally log in because it's going to require you to log in using any Gmail account, including your UNCC account, which is what you guys, as well as my other class, found out when we used this previously. Okay. In order to figure out what group you're in, I'm going to throw you into the breakout sessions. That way you guys can talk with each other inside of those breakout sessions. Okay. And what you're going to be asked to do is play around a little bit with the permutation functions. So before I throw you into the breakout sessions, anybody have any questions so far? Okay. The last question in the directions on these sticky notes that you'll be able to see once you zoom in is a question that is also up on poll everywhere. I'm going to go ahead and initialize this one. And this particular poll was really initially created just so that I would know when you guys had all finished your work over here. I still have it up there, but if you don't want to enter it in, I guess you don't have to. But it would also be a clear indicator to me of when we're done as well. But we're just going to do this activity for the rest of today. I think based on the time that it'll be close to the perfect time. I am not seeing anybody ask any extra questions, so I'm going to go ahead and throw you guys into your breakout sessions. Remember, as normal, at the top of the breakout screen, it will tell you you're in breakout session 1, 2, 3, or 4. Match that number with where you're at over here so everybody in your group can be working in the same location. Okay. You only need to have one person in your group be able to access this board, but I think it's probably going to be easier if everybody can. So I'm going to stop sharing this just so I can send this into breakout sessions, and that is going to start here in just a second. I started wrong. There we go.